Okay, so let's start. So buzzword in this title are low power, not buzzword, really useful. Embedded intelligence, buzzword, I agree. Emerging devices, useful for scaling. And new design paradigms using neuromorphic architectures. So I'll try to show you today how we have been able to address the low power circuit challenges through different applications and really addressing the architecture, the design, and the device level. If you look at this stack here, we have been able through years to address different architectures for the cloud, which is more multi-cores, multi-CPUs, edge fog. So here yet we'll start to have some power challenges, and then end devices. So end devices, we know that we have a lot of power challenges. Why? Because we want to have autonomy. In any case, in this stack, we have some thermal issues, and all this is limiting a lot the performances of the circuit. So not only the power, but also the thing that we have is that we have a lot of variations at each layer here, limiting the overall circuit performances. What does it mean? It means that if we want to push the circuit performances at any time, we have some limitations because we have a lot of variation. It means that we are never expecting the real performances that we have in a circuit in the end. So it's really important to consider low power in terms of energy efficiency. It means that whatever is the performance that you want to target, you still want to have the minimum power according to the variations limiting your application and your architecture. So for this, something really interesting and kind of intuitive would be to have systems that are really adaptive. So adaptive means that systems are flexible, adaptive to what is happening in the circuit, in the application, in the architecture, and able to provide the optimal performances in a circuit. For this, you need to take into account all the level of abstractions. It means that from application down to the technology, you need to bring adaptivity and flexibility to the circuit. It means that you do not want to have a single technology with one performance. Maybe you want to have many different performances available. You don't want to target one point of operation, but maybe a range of operation depending on the application. So for this, what you want is high energy efficiency. It means that you don't want to necessarily push the speed or reduce power, but for a certain speed, you want to have the minimum power. Of course, ideally, you would like to have this in an automatic way, dynamically, of course, because these variations are happening dynamically during the computation. So it can be kind of static, but most of the time, if you can modify and adapt your system dynamically, you have a huge gain in energy. Of course, this is what we can call auto-adaptive circuits. It's the optimal way to do it. We need to consider that variations are not only technology, but also environment. It means that when you are looking at end devices, you can be in very unpredictable environments. For example, if you are recovering the energy from the environment, then things can change a lot, and you are maybe not recovering the energy that is expected. And of course, if we push this paradigm to its natural, I would say, natural implementation, intelligence is the more adaptive thing that we can have because human beings are really adaptive by nature. So I think that you are already adaptive to your environment, to your intrinsic variations. And this is automatic and it's kind of high energy efficient. So this is what I'm pushing when I say embedded intelligence is ready for going more adaptive, more flexible. So my talk today will address different ways of adding more adaptivity and flexibility into architecture and design. The first is we can look at architecture and for different applications, so multi-cores and IoT devices. So today I will more address multi-cores. How can we bring more flexibility to these architectures in the way to have more energy efficiency? It's always the objective. Of course, at the moment, so with the Moore's law and the scaling, the multi-cores will have more and more variations, and adaptivity will have some limitations. Then we can go to more interesting architecture using 3D devices, and I'll show you how we can have more flexibility there using interesting network on chips and more architecture that are memory-centric. I'll show you how we can increase the performance there. And the third part of the talk is really dedicated to embedded intelligence. So what does it mean to get inspiration? So I don't want to mimic the brain, but I'd like to get some inspiration from the brain to have adaptive circuits and using new devices. So first part is dealing with architecture and design. So first thing really important today is when you look at the architecture, if you want to run the full multi-core system at the same voltage and frequency at the same speed, then you have a lot of issues. The first is it's difficult to, of course, to distribute the clock. The other thing is if you consider that you have some variability in your circuit, probably one core is not functional at the same speed and power from another core. So you need to consider a partitioning of the architecture where you could have cores running at different speed. But at that point, when you consider cores that have speed at different speed, then you need to consider how these cores are communicating together and how to do that in the best way. So one of very interesting architecture for that is what we call globally asynchronous and locally synchronous architecture. So what does it mean? It means that here you have all these islands in different colors that are running at their own speed. It means that in case of variability or power management, you could modify the voltage and the frequency of these islands separately and independently from another. Then you need to consider the synchronization between the cores. And here what you can have is a system that is globally asynchronous when you resynchronize with the communication and locally synchronous. This is what we call the GALs. We have different ways to implement this. So one way is to use asynchronous design. So why asynchronous design there? For the communication, I mean, not for the core. Why asynchronous design is interesting there? So you have this view here, which is showing very well the robustness of an asynchronous circuit to variations. So in a synchronous circuit, you have these people giving the bucket to the neighbor at each tick of the clock. Okay, so it's working very well as long as nothing is happening and as long as you have enough time to give the bucket to the neighbor. It's the slack time. In an asynchronous circuit, it's this line here. What you have is that the protocol for communicating data is based on handshake. It means that you communicate the data, the bucket here, to the neighbor only when the neighbor is ready to receive it. So it works very well, whatever is the variation. So why whatever is the variation? Because you can think that one guy here in the line is encountering a variation, I don't know why, a fly or something, and then is not able to get the bucket. Then the neighbor will wait as long as this person is able to get the bucket. So it means that whatever is the variation, the circuit will always be functional at the cost sometimes of some more delays. But in terms of robustness, it's really interesting when you think about different islands communicating together at different frequencies. Then you can synchronize really easily. So when we started, or where the community started on globally asynchronous and locally synchronous circuits, the first very interesting things for reducing power was the frequency scaling, because here, naturally, you can have different islands running at different frequency, and it's just really easy and natural to have the communication together with the asynchronous system. So the first implementation we had was first to design this asynchronous network on chip, bringing the robustness to the synchronization and to the network on chip itself. So it's kind of really simple here. You have a 2D mesh structure. The network on chip and the node of the network on chip are performing all the asynchronous communication. And what we have here in terms of design is what we call quasi-delay insensitive. So it means that whatever is the variation due to voltage supply changing, temperature changing, the circuit is always functional. There is one basis hypothesis that we ensure by construction when we design the circuit. We have specific encoding and protocol. This is for the handshake. So you remember that we don't have clock ticks. We have this handshake. And this, we first demonstrated it some time ago. We already have a lot of generation of it. And what is really interesting is when you go from one technology to another, whereas in synchronous circuit, it takes time, it's difficult. Here, it was always functional, so sometimes not always optimal in terms of performances. But it's really interesting to see that here, intrinsically, you have the robustness for the variations and for porting to different technologies. So in this first circuit that is shown here, naturally we had 24 clock domains corresponding to 24 IPs running at 24 different frequencies. And we were resynchronizing the data from one core to another just by using this asynchronous network on chip. So here, at that time, it was 130. We had about less than 20% dynamic error, but already it's an interesting number if you consider a multi-core. So one more step now. So we have seen how to manage the voltage, the frequency. We have also been able to manage the voltage of each island, because remember, when you are doing frequency scaling, you reduce the dynamic power, but then you need to go through voltage scaling to reduce the dynamic power quadratically and the leakage power as well. So if you consider an architecture now doing what we call DVFS, so dynamic voltage and frequency scaling, you have the core here. You modify the voltage and you modify the frequency. Okay, it works very well. Everything is resynchronized by the asynchronous network on chip or in another frequency, but in a Gauss way. The thing is that if you consider advanced technologies, it's really difficult to set this voltage and frequency point, because you can set it, but during computation, you will have some voltage drops. You will have temperature variations that are local to the chip. You don't have a lot of process variation except for aging, but you need to manage what we call the PVT variations. And this is not easy just to set the voltage and frequency point, because you remember, to reach this high energy point, high energy efficiency point, we need to set these two parameters according to what is happening in the core. So this is what we call adaptive voltage and frequency scaling. So what does it mean? It means that in addition to the actuators that you have to modify the performance of your circuit, that are here, the voltage supply and the frequency, you need to add some sensors inside the circuit, giving you an information of what is happening in the circuit. So interestingly, when we started all this, we had in mind to have some sensors. So usually what a digital designer do when she or he wants to have a good sensors are going to analog designers and then provide wonderful temperature sensors, which is twice the size of a core. Okay, great. So we had the same issues when we wanted to have local frequency generators, because we went to go people doing RF and they were providing a wonderful PLL, which was maybe 10 times the size of the core here. Okay, so we've been able to go finer. So the interesting idea here is that we don't need to know the absolute temperature. We don't need to know the absolute value of the voltage. What we need to know is that these values are changing. So really simple sensors giving you a dynamic information of what is happening in the core is really enough. Then, when you have this information, you need to extract the real information. What's the PVT information and how is it changing? And then you have a local loop that is adjusting the voltage and the frequency according to this information of the sensor. So the main target is your application, but according to this information there, probably you can monitor the voltage and frequency to reach this high energy efficiency. Okay, we don't want to reduce the voltage for reducing the voltage. We want to reduce the voltage according to a target frequency, which is usually constrained by the application. So we have DFS, just modifying the frequency of each course. Having a Gauss architecture helps a lot to have this. Then we move to DVFS, that I didn't show here for a question of time, but here it means that you modify the voltage and the frequency of each core, and you still have this Gauss architecture. Then to go to adaptivity and to limit the impact of the variations, we go to AVFS, which is adaptive voltage and frequency scaling architecture. So we modify the voltage and the frequency according to intrinsic PVT variations and dynamically. So really important is this dynamically. Okay, so at this step, we already had some interesting architectures that are used a lot today by many multi-core processors. So what is mainly due today when you have a very large multi-core running at, I don't know, 3, 5, 4 gigahertz, they need to manage the voltage storm that they have at the starting. So usually this is really done for that, to manage the starting point. But then during operation, you still have some information to track, and mainly the voltage drops are something really important to track. So we do not only have sensors that are just giving a PBT information, we also have some information that are inside the critical path of the circuit using some kind of razors. So it's what we call timing fault sensors. But here we don't want to detect a fault. We want to anticipate the fault. So remember, we are in an adaptive system. And this is what is difficult, because you need then to detect a voltage drop in less than 2 cycles and then being able to feed back the information to improve the performances. So something interesting. So what is important is that at CEA-Leti, we have a design and architecture division, but historically, the technology division is really leading our research. So for years, we have been pushed to go to more new technologies and also to use FDSOI, which has been developed originally by Leti. When we were thinking about all these adaptive things, people were coming with FDSOI and say, oh, look, we have something really interesting in FDSOI. We have this back bias that is just available because you are able to bias the backplane of the transistor here. And what it brings is, if you increase this back bias, you can go either to very high VT transistors, it means that you can lower the leakage, or you can go to very small VT transistors, it means that you can higher the speed, increase the speed. And if you think about these adaptive systems, compared to what we have in classical bulk, this is limited by the diodes that you have in bulk. Here you can go, so theoretically, you can go to plus minus 3 volts. In practice, we have been able to go to 1.8 volts. And in reality, plus 1 volt is already something really affordable for leakage and already boosting a lot the performances. So if we look now at our adaptive architecture, what does it mean? It means that here we have a new actuator. And this actuator is the back bias actuator. It's not in the same dynamics than the voltage supply and the frequency, because when you modify the backplane of your architecture, you need to charge all the capacitance of the backplane, and it takes time. So it's another point of optimization, but really clearly it helps to find a new way of adapting circuit. And it's extremely efficient at low voltage, which is really interesting, because usually we want to go low voltage because we know that it saves power, but at low voltage we are really limited in terms of frequency. So this is what we have demonstrated here with the DSP, 32-bit DSP, so really simple. What is first interesting to see in this figure here is that we are able to run at low voltage at very high frequency. Secondly, what is interesting to see here is that if you consider the adaptive scheme here, you have, if you fix the frequency, which is usually what you want, you can have a gain up to 20% when you modify the back bias. So the different colors here are the different values of the back bias. Of course, it will be at the cost of the leakage, or it will be at the cost of the speed. It depends. If here your target is to have a fixed energy budget, which is sometimes the case in some applications, then you're able to increase a lot the frequency, and it's really efficient mainly at low voltage, not sub-threshold, but near threshold voltage, or even lower than nominal voltage. So this brings a very high flexibility. So I think here I showed you how we can bring more flexibilities to classical architectures that are digital architectures with multi-cores, so bringing new actuators with new technologies. So it means that scaling will give you a lot of variability. We know how to manage it at design and architectural level. Technology like FDSOI can bring you one more way to adapt your circuit, but there are some limitations. Here we are now. So if we want to push more the performance, the idea is to use 3D architectures. So what kind of 3D technologies do we have today? So we have the kind of 3D technology that is die-on-die, what you called through silicon vias or TSVs. And the pitch that we can fabricate with that, so when I say we, it's not only CEA-Leti, people are providing that already in fabrication. It's around a pitch of 20 micrometer. Okay, it means that if you want to stack dies on dies, it's kind of feasible, but the grain of stacking is quite coarse. If you move now to more dense interconnect, you can go to hybrid bonding, which is mainly done today by copper to copper. And here you can see that the pitch that is feasible is 2 to 5. We have even demonstrated now some hybrid bonding with 1 micrometer pitch. So in terms of interconnect density, it's already quite high. So here you can either have wafer on wafer or die on wafer. So already here you are increasing the number of interconnect. So in terms of partitioning of architecture, it brings you something new. It means that maybe a partitioning inside the core, so block per block or core per block or SRAM on logic is something that is more feasible. And if we push the density more, we can go even to what we call so monolithic 3D, sequential 3D. So there are many different names for that. At Leti we call it cool cube because it's a cold process to fabricate it. And here, when you look at the pitch, it's really small. It's 0.1 micrometer. It means that potentially you could stack a transistor on the top of another transistor. So okay, this is technology. It's great. So you can see here that the story of what I call 3D stack at CEA-Leti is not starting today. So it started some time ago already. We have always tried to have some companies helping us in going this way, in going 3D. And if you look at this slide that I will not detail today, what is interesting is that after all these years, we've been able now to demonstrate some real circuit and architecture. So what is really important with that kind of flow is that usually people are providing very interesting technologies. And at the time they come and they say, oh, we have a wonderful 3D technology and you can have this pitch and okay, what are you doing with that? So as designers and architects, usually people, what they do is, oh, we have a 2D design, let's put it in 3D. Most of the time you have no gain. It's really clear. And as well, when we were designing synchronous circuits, people came and said, oh, you should design that in asynchronous. Okay, but synchronous versus asynchronous, no gain. But if you think about the architecture and the functionality, okay, asynchronous can help in GALs, for example. And here, the same idea. The idea is you have more interconnect. The interconnect is more dense. So what does it mean in terms of architecture? It means that each time in your architecture, your limitation is the interconnect, then you can start thinking 3D. So for more flexibility, if we want to have more interconnect, more control, more data communication, thinking 3D can be already a good starting point. So I'll show you what we have. So still in mind flexible architecture. So I will not review all what we did in 3D and all what is done, but still thinking flexibility. Something we demonstrated that is really interesting. So you remember this globally asynchronous and locally synchronous architecture. And we have this asynchronous interconnect. So in 2D, it's really convenient because we don't need to distribute the clock on the full chip. We just distribute the different IPs. And something interesting happening when we started to do the 3D. So people came with the technology. You have different stacks. It's wonderful. And the first question we had was, wow, but how can we communicate between the top tier and the bottom tier? Okay, we have kind of same technologies, but then we need to communicate. We have no ideas about the performance of the TSVs themselves. So something quite natural was to think about using this asynchronous network on chip. So you remember we have the handshake at the interface, and the handshake can be performed in the protocol using the 3D, and whatever is the delay that you have due to this TSV, or if the TSV is really bad, then you still have the functionality of the communication between the top tier and the bottom tier. Something really interesting that is shown here. So here is the asynchronous NoC that we had in 2D. We put it in 3D, and on the top of it, we have some processors. So it's really multi-cores. under fabrication now, we have even 96 cores that are fabricated and stacked on the top of them. Something interesting is this curve here. So what we've shown here is we have different links in the network on chip. We have tried different links with redundancy, with tests, no tests, and so on. But what is more interesting is that we changed the temperature from the top tier to the bottom tier. So it means that we mimic a large variation, but in reality, we also have some thermal issues at the interface. So it's really something that is real. And automatically, without any control, the data throughput of the network on chip is modified according to the temperature changing. So this is really something that is showing just flexibility, stacking, and natural adaptivity to what is happening in a 3D stack. So now, if we are going more dense, I would say, so something interesting is when you talk about 3D, some people you can always talk to are image sensor designers. For them, it's really convenient to build everything in 3D. First, it's natural because usually they have the sensor and the electronic that is already stacked. And they always think about putting more computing in the pixels, in the columns, and so on. So these people are always very attracted by these 3D technologies. Something interesting is, here again, people started thinking about imagers in 3D, but just by having the 2D imager and providing it in 3D. So what happens in this case? So when you have an imager, you compute all the columns, and then you get the information from the columns. And in 3D, you compute the columns, and you process the information on the bottom. But finally, the frame rate per second is still the same compared to 2D, except that, OK, you have the SRAM on the top, or you have the computation on the top. So in terms of area, it's more interesting. But if really you want to think 3D and parallel, the idea would be to directly compute the information from the pixel or from a group of pixels directly in the bottom. So this is what we did in this circuit that will be presented and demonstrated this year at VLSI Symposium, so in June, if you want to come in Hawaii. So yeah, you see? So it's a two-layer 3D stack BSI, so backside illuminated vision chip. So what does it mean, vision chip? It means that you have the sensor and you have the computation. So something really important to see, and that you will see here, is that you have all the array here. And for each macro pixel, so we call it macro pixel, we have some computation on the bottom. Something interesting here is that we do not only have the information from the pixel to the computation, but we also have some feedback information to control the electronic around the pixel. So it means that on the top we have pixels, ADC, and the computation on the bottom. So what does it bring? So naturally, if you have something that is fully parallel, the frame rate per second is not limited. It means that here we've been able to obtain 5,000 frames per second. Some people are getting this also, but what they do is that they are reducing the resolution of the ADC. So it's kind of fake. Here we never reduce the ADC resolution, and we still get the high frame per second. This is exactly what we want when we are doing some parallel computation with a high density interconnect. So I like to show this figure because they always have very nice picture in the 3D technologies. So here you see the imager and the stack. So here you have the photodiodes. Of course, we need the photodiodes to backside illuminate the chip. And here you can see the vias, so the copper-copper bonding. And on the bottom, we have all the mixed signal designs going there and all the 3D connectivity. So an important figure that you need to have here is the number of signals and the number of interconnection that you have. So here it's more than 6,000 signals, which is a very high number. So imagine in 2D how to be able really to route all these and all these wires. Here it's kind of natural because you have the 3D stack. So improving the parallel computation using all the wires and increasing the frame per second. This is exactly what we would expect from a 3D architecture. So then, if we are going to really dense technologies now. So what we call 3D monolithic. So we are able to have a stack transistor on transistor. So it's really fine grain. So yet, as a designer point of view, it's kind of difficult to really know what the benefit will be to have a so dense interconnect, because already with the hybrid copper to copper, people are really interested. But finally, if you want to push the architecture, to have more interconnect and to think about the computing as something which is close to the memory or even inside the memory, this very dense interconnect will give you all the information close to the computation. And this is what we will explore. So here again, the same picture just to tell you that the 3D monolithic is yet not something new at Leti. You see the picture here is more dense than what we had for the 3D stack. Of course, it's less mature technology. But yet, if you look at it here, we start to have some first circuits, and we already have some tape out running. So we'll be able to demonstrate some architectures using very high density 3D. But of course, it takes time. It's not 8 tiers, it's still 2 layers. Of course, we would like to have 7, 10, 8 layers, but the technology yet is not mature, but we can think about very nice perspectives for that kind of architectures. So one first perspective that we think about is what we call memory-centric architectures. So this we are working in collaboration with Stanford. And the idea is really to use this high-density interconnect to go really close to the memory, close to the computing and the memory. Something fully parallel. It's really something that we call memory-centric architecture, which is different architecture that we used to use. There are different things that we are exploring here. So first is, you know that now we can have access to the computation inside the memory. This is what we call in-memory computing. It can have some benefit to design this in-memory computing in 3D. This is what we are currently exploring at architectural level. Of course, the idea is then to extend this capacity that we have inside the memory and 3D, extended to more computation using maybe some simple operation. Yeah.
So are you doing the bench-top style instruction sets that NYU and IBM tried to do?
In the IMC, you mean?
Yeah.
So the IMC, you have different ways to do it. So you can have bitwise. Okay, so bitwise is just OR, NAND, and XOR shifts. Then it's really useful for kind of security applications. If you want to have multiplications, you need to go to more analog arrays with Kirchhoff laws. Okay, but in theory, you could have access to all the arithmetic that is available in a memory. Then, of course, you need to program it, and you need to think about the architecture using the memory as the computation. So, of course, in terms of programming, it's something different that you need to handle. The idea here is really to show, because what we discuss a lot is, okay, we have this computation in IMC, but very good digital designers with a good technology will maybe do something that is better or even more interesting. But when you go 3D, things are changing because maybe you can get the benefit of both. You can get the benefit of 3D, having the memory close to the computation, and you can maybe get the benefit of the computation inside the memory. So I don't have the answer yet, but this is really new architectures that we are looking at actually.
Well, things were certainly, I mean, IBM certainly tried to sell some machines to a few dozen customers in the late 80s.
It's different grain. It's different grain of stacking. Okay, so here we are not talking about HBM or whatever. It's different grain of stacking. Okay, it's not.
I mean, IBM would work with Notre Dame and Peter Krogi on the processor and memory stuff, and they apparently built some number of machines with them. But also, they did a separate direction with NYU using the Rio and IBM 6000 series CPUs as well too. It's a matter of granularity, is your point.
And you know, also the name processing in memory has been used for so many things. Usually, what we say is processing in memory is more near memory computing and HBM and so on. This is usually what we used to say for processing in memory. What we call in-memory computing is really the memory able to perform some computation. And then memory-centric architecture is we have the computation really close to the memory. So in all these landscape, I would say there are so many contributions that are interesting to get and to see how 3D can help for that. So this is what we are currently exploring. So just to give you the full picture, which is really something that we are just exploring now, the idea would be to be able to stack some computing and some in-memory computing on the top of it. And why not inserting some non-volatile features? We could help to have more density, but also could help to have different applications in that kind of objects. So I've been through these different 3D technologies and how it can bring more flexibility, more performances, and how we can think 3D when we think about architecture. Something really important now also is to, if we think about this really fine grain, we can think about the way the brain is constructed. And you know that the brain is by nature formed by 3D cortical columns, and it's the basis of learning. So why wouldn't we take advantage of this 3D with a very high interconnect to try to have more performances in learning? So we are not there yet, but it's kind of inspiration that we try to get. And something else is thinking about more than two stacks. We could think about image sensors that are really be able to stack some image sensor, analog computation, and then memory, and then computing. So here really you think about the full stack and all the computation and the analog in the different stacks, and the performance will be really improved. So I've been through architecture and design, 3D architectures, try to think 3D to maybe have more performances, more functionality, new applications. And I'll try to go now to what I call embedded intelligence, which I think is, of course, the optimal way of doing some adaptive circuits. I will mainly focus on spiking circuits and new devices. So the reason for that, so I know that there are a lot of discussions on spiking neural networks and so on. But once you want to link new devices and neural networks, linking new devices with spiking is kind of something which is really optimal, because if you try to mimic the spiking in a synapse with an RRAM, it's exactly the way it works in the brain. And also you will see that 3D is really convenient to interconnect all the spikes coming from the sensors with the computing. So here, the idea is not to mimic the brain again. The idea is to get inspiration from the brain for more flexibility. Because if you think about learning, it's the way we ourselves, we adapt to the environment, because we learn. And once we learn, we know how to adapt to any variations that can happen. It's interesting to think about embedded learning, because what we want to show, you remember this high energy efficiency. I'm still in the low power landscape here. It's difficult to bring big neural networks to end devices. It consumes a lot of power. You can do training and inference, but in reality, we really need to provide that to end devices, because we need to have this learning. It can be of many different sorts. It's not necessarily neural network. It can be reinforcement learning, but in any case, it will give you some contextual information. It's a scheme that is fully event-driven. So you remember that we have a lot of experience on asynchronous circuits. So this event-driven scheme is really convenient to asynchronous circuits. It's fault-tolerant to have some embedded learning, and low energy. So this is really what we would like to get from the learning. So after this slide, I have a movie which is merging all the technology. Which is merging all the technology with the, sorry, which is merging all the technology with what we can do with neuromorphic. And from this movie, I will have 3 key messages, but I can run the movie first. It works.
Institute located in Grenoble, France. Inspired by the human brain, whose computing efficiency and low power performance still remain unmatched. Leti is developing novel neuromorphic systems using optimized emerging CMOS technologies. The brain and spinal cord form the central nervous system. The brain processes and coordinates the body's activities using information from the sensory receptors. Neuroimaging has revealed a multi-layered brain structure with an outer, reconfigurable cortex area and subcortical hardwired core. The cortex is composed of a very big number of large-scale neural networks, arranged hierarchically in horizontal layers and vertical columns having dense modules and sparse overall connectivity. Neurons are the elementary building blocks of neural networks. They communicate by way of action potentials, or spikes, which propagate along axons and accumulate in specialized regions called synapses. Transmission across the synaptic gap is accomplished by chemical messengers, called neurotransmitters. Connections between neurons are altered in response to a stimulus. The persistence of these alterations is the biological basis of human memory. Learning requires synaptic plasticity, which refers to the capacity of change in the synapses structure. Inspired by neuroscience and the functional principles of the human brain, Leti's scientists are developing innovative low-power systems by implementing optimized special-purpose hardware fabricated on 300mm wafers. Novel emerging technologies are being used for the synthesis of smart systems. Artificial neurons are being manufactured using specialized CMOS circuits based on fully depleted SOI technologies, with a mixed-signal design approach. FDSOI technologies, pioneered by Leti, have proven to be suitable for ultra-low power design. Non-volatile resistive memories are promising components to simulate synaptic behavior. Leti is developing resistive random access memories, such as phase change memories, conductive bridge memories, and vertical oxide-based memories. The variation of their resistive state enables information storage. These technologies offer non-volatility, precise conductance modulation, and high density of integration, needed to model synaptic behavior. Based on the columnar organization of the brain cortex, Leti is integrating FDSOI circuits and resistive memories monolithically, using an extremely dense 3D integration technology called CoolCube. Active device layers are stacked sequentially using very low thermal budgets. This makes it possible to obtain very small 3D contact pitches of the order of 100 nanometers within and between the different tiers. Less dense 3D integration is also possible with more technologies, such as through silicon vias coupled with hybrid bonding techniques. These allow for high parallelism and energy-efficient computing. The use of photonic waveguides to connect networks across long distances offers high speeds, high bandwidth, and low crosstalk. The central nervous system is connected to our senses: seeing, hearing, touching, tasting, and smelling, and to our emotions, thoughts, and memory. Similarly, extremely low power, context-aware, multi-module platforms with spike-based neural networks can be directly interfaced to bio-inspired event-driven sensors for image, audio, tactile, and chemical sensing. Brain-inspired hardware, coupled to new computing paradigms, will exploit the full potential of new disruptive technologies and address the enduring power efficiency issues of traditional computing architectures. Distributed intelligence will span the whole IoT network, sustaining our hyper-connected society and benefiting individuals worldwide.
Okay, so 3 key messages from my perspective. Of course, there are many key messages there, but the first one is, if you look at the brain, the computation is fully distributed. Clearly, you don't have access to a mass memory, you get the weights and so on. It's fully distributed, everything is in the synapse and in the neurons during the computation. And probably it brings a lot of efficiency. Power efficiency, I don't say low energy, but energy efficiency. Second thing is, everything is working with spikes, and probably this brings also very low energy. Providing data with spikes and interval between the spikes give the information. All the sensors that we have are providing spikes through the brain. So it means that our vision sensor is not at all a camera providing an image. Our vision sensor is providing spikes. And then the brain is able to recover all the spikes and fabricate the image. Third message is, by construction, the brain is really interconnected. And the more you learn, the more interconnections you have. And this is really done by 3D cortical columns that you can find mostly everywhere in the brain. And these columns are really the basis of the learning. So the idea is to see how we can use this from the brain and use new emerging technologies to see if we can bring some more intelligence in the IoT device. So the idea is low power, efficiency, of course. So the first thing that we are working on are resistive RAM. So you've seen in the movie that we have many different resistive RAM. So I won't go through the details of the technology here. But the idea is to think that we can use these technologies as synapses. It can have exactly the same function as a synapse. So this is what we are currently demonstrating here. So we still don't have the chip, but what we did here is to build the synapses as RRAM and then have some computation. So it's a really small application here, but the idea is really to use the spike at the input and to perform some simple application, really showing that we can build the synapses with the RRAMs. Second thing that is really interesting is that today a lot of sensors that are claiming to be low power, it's not always true, but it's still a good start, are providing some spikes. It means that, for example, on an image sensor, instead of providing the image, when you just have a changing in the image sensor, you provide a spike where the pixel has changed. If you think about tactile sensors, they are providing spikes. If you think about artificial retinas, they are providing spikes. There are many sensors today that are providing spikes, cochlea also. But what people do is that they have the spikes. Most of the time, the information is coded in the time interval between the spikes. So what people do is that they are doing time-to-digital converters, and then they are able to compute all the information in digital with classical DSP. Of course, it has a cost. And here again, it's just thinking about, okay, how can I do computation? I have a good digital DSP. Okay, let's put around everything to convert to something that is interesting for me. But this has a cost. So the idea is that we have designed a DSP that is just using the input spikes, using the precise timing between the spikes, and here we are able to perform a lot of operation, so more than a classical DSP, because by construction, when we reassemble the different neurons and the different types of synapses together, we are able to perform a lot of operation, nonlinear operation or whatever. And by nature, this DSP is approximate. It means that when you want to reduce the number of bits, then naturally the power scales. It means that now we can interface directly a sensor with a DSP, and this DSP is directly computing spikes. So be careful here. It's not a question of neural network. Okay, we are using neurons to compute the spikes, but to perform computation like a DSP. So we already have some good results, even if the picojoule per synaptic event could be lower, but we really showed the functionality of an audio processing. It means that we have a data set coming from ETH at Zurich, and they provide all the information from an artificial cochlea, and we have been able to process all the information directly from the spikes, and at very low cost compared to a TDC plus a DSP. Okay, so now, if we move to more to the future, I would say, so I will just show you two works in progress just to show you the objective and what we are targeting, and it will be the end of my talk. So first is we try to work on 3D cortical columns. So we have not started yet, really, but we'll start with a Stanford student and some people working at Leti. So the idea here is if you look at the cortical columns in the cortex, they are clearly 3D. So if you look here, you have different stacks. what is really interesting is that compared a new baby born, and I don't know, it's 2 years or more, the more you learn, the more the interconnections you have. But not only that, the more you learn, the more the function of the neurons in the different layers are changing. So it means that if you can think about having more interconnections, being able to reconfigure the types of neurons between the layers, probably you will improve a lot the way you can learn in a circuit. Of course, at this step here, what we will just consider is trying to improve so we have some sensors providing some spikes, and these spikes are computed by the cortical column. So we will first try to look at the first level here, trying to interconnect all the spikes to the first neurons and see what we can have already. So it's the first step, and we'll try to tape out this circuit at the end of the year. Something else, if we want to go to more dense 3D, we are working on spiking vision system. So here again, the idea is to have an imager that is a spiking sensor. Another layer which is able to do the mixed signal processing directly using the spikes, or maybe just translating the spikes into a digital system, then providing all the memory that we need and all the computation. For this, we need a lot of layers. So this is what we are trying to manage now. And of course, on the top of it, we need power management. And remember, here again, we need to manage the power, the variability. The more stacks you have, the more functionality, but the more performance limitation. And that's it for today. Thank you.
Your network on a chip, you didn't seem to elaborate too much. Presumably, you're doing your own protocols on the chip. You're not trying to do anything like revamping TCP/IP.
So there are different levels of protocols. So the physical protocol is the handshake. On the top of it, we have virtual channels, which is a classical NoC protocols to avoid congestion. And it's, you see, here it's architectural protocol, NoC protocol. And in the bottom, we have physical protocol, which is the handshake, which is replacing the clock tree. Okay. Questions?
How much do the device characteristics vary over the temperature range during normal operation?
For which devices?
In the multi-layer unit.
In the TSVs?
Say in the vision application.
Mm-hmm.
Do you have? I mean, it seems like there are issues with thermal expansion of one layer.
When we stack.
And if they're firmly bound together, then there's strain issues on device characteristics.
Also electrical timing.
Yeah, of course. So the vias themselves, they are more sensitive to the alignment that we have during fabrication. But after fabrication, we have some thermal issues, and it's considered as a variation that we need to handle dynamically. But as in a transistor, we have some PVT variation that we need to handle. Then we add some variations on the via itself, but it has to be considered in the full flow and in the architecture and in the power management. Okay.
Very nice talk, Edith. I have a whole bunch of questions, but I'll limit to 2.
To 10. Don't tell me that you don't like spikes, no.
Well, it's a question of the level of abstraction you present to the user, because users don't like spikes. But anyway, that's a separate question. I like them, but I don't know about my users. But the question had to do with the first one is, so you talk about edge computing. Can you be a little more specific? So do you have, or maybe you don't have right now, but do you have really a more concrete target application at the edge where you think this makes sense? Is it, or is that still fuzzy?
For end devices, it's more clear for me that it's sensing applications, different type of sensing. At the edge?
Yeah, what kind of sensing? Like, what would it do, and what would it do with the smarts that it has?
Yeah, at the edge you can have a multiple sensing that could be image sensor, wake-up RF, so sensing the channels that you have around to communicate in wireless. It can be tactile, depending on your application. It could be audio. it can have many different ways of sensing.
Each of these devices is kind of like application specific. It's doing some, pretty specific thing or what? Yeah.
I think that the most interesting thing we could provide is to provide a contextual information with all the sensors together. This is what we call multimodal platforms, meaning that, okay, you see something, but you just correlate with what you hear, and here I know where I am. I'm not at Leti because I see you, or I'm not at home because I see you and I don't hear my kids. And all this contextual information, if you can bring it really at the edge or at the end devices, then the information you get from a sensing platform is really interesting. But then you need a lot of sensing, of embedded learning, many things. So usually you target one application, it's easier in terms of power, instead of getting everything.
What do you think, what power budget do you think you have to meet for this?
Power budget for one end device? Yeah. I would say when you talk about microwatt, I like it. Yeah.
I like that too.
Yeah.
I mean,
Tens of microwatts, still I like it. Edge you can, yeah. And as soon as you have a wireless communication, you need to start to milliwatts or tens of milliwatts, okay? But if you consider the edge, maybe you're plugged, so maybe you don't need to have energy harvesting or whatever. So then milliwatts is something that is affordable for edge, I would say. And as long as you have wireless communication, of course. Well, I've tried to push wireless people to go down to microwatt, but they don't want to.
Yeah, but anyway, the second question, that was just the first one. So, I believe in you guys had an IEDM paper on a ferroelectric, non-volatile memory, which, seems like it's going to be available in 22 FDSOI. And so you didn't mention that as one of your devices there. How does that compare with?
Yeah. So I think it's more an AVES memory that we have. I think it's the AVES that I was presenting that we are trying to build on the top of a DSOI now.
They used to do this with PZT, and now they have some new
PCM
material.
then? Phase change memory?
No, PZT.
Ah, yeah. Yeah, I don't know. So
yeah,
no, I don't know this particular device. People we are working with are already working more on AVES.
Okay.
It's kind of more reliable from what we know, and we've been able to.
Some early work in Leti regarding FDRAM,
RAM.
This is just starting, and there is a new project starting, and we have some information, so I can put you in contact with the right people.
Yeah, I got an email from Seven Bias at present.
We're not in contact.
Yes, I don't know the detail, but I can bring you some.
But of course, the idea is to have the best non-volatility with the best reliability and with everything. So whatever is the device, we need to figure out how to use it at design level. It's a transistor, yeah. But in any case, it's the question I had for Alex at the end of this talk. So what will you do if you had non-volatile resistive memories that are very good? And this we need to figure out because, of course, the devices are not coming always in 1 month or 2 months, but it's still interesting to figure out at the architecture and design level. Yeah.
Are you considering any sort of error detection in your asynchronous communication connectivity?
So in the cores, we have some error detection. So it's not error detection, it's anticipating errors because we have this adaptive scheme. So we need to know where we are in the critical path with respect to the slack to be sure that when we are starting to get this margin of the slack, we really need to modify the voltage and the frequency because it means that we are really in the dangerous zone. So we are correlating the PVT sensors with this error detection, which is what we call timing fault sensor. It's razors with some methodology around, but it's kind of razors. And then we are able to modify the voltage and the frequency accordingly. Of course, it's really the basis of AVFS systems.
With your architecture, you can kind of emulate some biological sensors and things like that, but have you tried to emulate hearing or sight or smell or anything yet? And how fast can you do it?
No, really, no. No, really here we are more really focusing on simple circuits and systems. The full, I would say the full application and how the smells work and so on. No, we're not working on that yet. No.
And how fast what's the fastest rate that your asynchronous communications can talk to each other?
Yeah, it depends on the technology, but it's quite similar to synchronous. You have very good throughput and. So it's twice the latency and twice the throughput compared to a synchronous network on chip. You see, so you double the throughput and you double the latency, but then when you use it, the throughput is just giving you. Yeah, you reuse. Yeah.
He's asking for a hard number. So for example.
In bit per second, for example.
Yeah, like for example.
Like hundreds of mega asynchronous transfers per second, or.
Compared to what? Compared to a synchronous version?
Doesn't matter.
Doesn't matter.
For asynchronous communication, you mean? Is that what you mean?
If you put too many things in parallel and do it synchronously, it doesn't work because you end up with power distribution problems. If you do two things too fast asynchronously, you run into races.
Yeah, but here we're not doing computation, it's communication. It's the question. So is it the rate of the communication that you're asking for?
No. The rate at which you're trying to arbitrate.
Just give a number. For example,
don't give units, 12.
No, but I would like to give a number, but is it in megahertz that you expect? Or?
Let's say you have a synchronous NoC, okay? If you have a synchronous NoC, let's say.
Yeah.
So then you have two units, and you're communicating between them.
Okay. So in 28, I think we have around 500 megahertz.
Right. In 28?
In 28.
No, we are much above that.
Yeah,
so above 1 gigahertz.
So
it's the number that we have in 65 is 500 megahertz.
So slightly more of that, but
yeah, in 28 FDSI we have 1 gigahertz in throughput. Yeah. And the cores, they are just running at, I don't know, it depends, not 1 giga, but around the course, the computing itself. In 28, I give the number 28 FDSY, let's say. Okay, so your question is... Yeah.
Yes, you can think about gigabits per second.
Yeah. So your question is the communication limiting the computing performances, or?
You run into a barrier someplace when you go too fast.
Yeah. Is the communication limiting the performances, or are the core limiting the performances, right?
No, specifically I was wondering about your asynchronous communication. How fast can that occur without running into a problem?
If it's not fast enough, you mean?
It doesn't run into problems if it's slow enough.
I don't see the
If I may, I
don't see the question.
So the asynchronous logic can run as fast as it goes, and there will be no problem and no break-even point about the ISP, because it will go as fast at the gate as
are able to go, yeah. At the limitation of the protocol itself.
In terms of asynchronous logic, above 1 gigahertz very easily, and usually the clock is the limit. So actually, we are not able to feed the asynchronous pipeline as fast as we could. So we are just limited by injecting traffic in that asynchronous logic. And
the FIFO that they interface
actually
at the
is a GALS interface, which is bridging between the asynchronous domain and the synchronous domain, where we are synchronizing between both pieces of logic. And this is where is the real limit. The limit is not within the asynchronous.
It's in the GALS interfaces, yeah. Because you have FIFOs, and on one side of the FIFO it's asynchronous, on the other side it's synchronous. So here you need to say. Not sure.
No, I understand how you're progressing now. If you do enough calculations and then you communicate, and you do more calculations and then you communicate, the communication is so slow compared to the calculations that you don't run into the asynchronous problems.
Okay, but it's a question of architecture then and application mapping and so on. So, of course, you don't do one multiplication and communicate in asynchronous with the NoC. Of course, it's not the purpose at all. We still have basic multi-cores architecture, so yeah, at the time we're...
Systolic, as I remember.
Yeah, of course. Systolic is different.
He will pump data as fast as he can.
Systolic is different.
It's not true systolic because you can't use clocks for a big thing, but you can still think that way.
there are people who will definitely pay for specialized systolic architecture. You don't have to ask.
I know. I think we talked about it all the day today. So I'm convinced.
The human genome is sequenced on systolic architectures. Most people don't realize that.
With those type of speeds and that kind of architecture, I could give you algorithms that would emulate your retina, and then you could recognize objects very fast.
Dynamically, yeah, of course, because you just get the rate. But then maybe so I talked with Ijesh Shilinsky working on artificial retina. So what he says is now the limitation is not really the rate of the spike that you can compute, but really all the first interface to the sensors, gathering all these spikes together. So we are still not yet improving in the CMOS part. They still have some sensor interface limitation for that.
Like I can ask you to recognize eyeballs or smiles or noses or hands or doorknobs or light bulbs or something, and you can do it pretty fast. The limitation becomes how many millions of things can I ask you to recognize in a second?
Yeah.
And it doesn't make sense to ask you what order.
Yeah,
it's a higher level thing that's needs organizing. It's not the sensor itself or the recognition circuit.
It's the whole system and the recognition. Yeah.
It seems to me that a lot of this still qualifies as being pure research with lots of potential and lots of work that has to be done to understand what can be done. Silicon Valley has a history of being more practically minded and working towards commercial products that can be sold to an established customer base to solve known problems.
Yeah.
What is the time frame? When do you think commercial products might emerge from the work you're doing now?
There are many different things in my presentation. So on the architectural level for GALs and power management, I think it's on the market now because everybody is doing AVFS, DVFS, and some people are doing GALs even if they are not using asynchronous NoC, but more and more people are trying to get to asynchronous NoC as well. And for the devices, so 3D, so one part of 3D is already fabricated, so you can have access if you want. Then for sequential 3D, the monolithic 3D, it's not mature yet, but it depends on how companies are pushing, but things are moving very fast, less lightly. So I would say that I would expect that the first maybe product in 3 to 5 years could be something that is feasible. It depends, of course, on how things are moving on the industrial side. And for resistive memories, there are already many resistive memories available. The thing now is to have more dense memories, being able to have multi-values inside, so less variability, maybe stack it in 3D to have more density, and so on. So yeah, there are different levels of maturity of all this. As soon as you are using emerging devices, it takes some years, of course, to get to the maturity. But for architecture, it can go really fast on the market and in products.
So how do I do useful work with spikes? I can think in terms of C compilers and ANDs and OR gates, but I haven't figured out what to do with spikes.
You're figuring out what to do.
I have not figured out what to do.
You have not figured
out. Yeah, what's the best way to program this?
I don't know. No, there are a lot of discussions around that. So people are comparing spiking neural networks and artificial neural networks. In terms of programming, it's really different. So there are some programming tools already, but it has not shown a full interest, I would say. If now you are going more to sensing, and here it's different because what we have is a spiking DSP, so the way to program it is just to program the framework on the top of it. It means that for an addition or a multiplier, we just program the DSP to say, okay, for a multiplier, you get these neurons, these synapses, you assemble it, and you run the operation. So there are really different levels of programming in your question. So I would say for SNN, people are working on programming models, but for really sensor interfaces, it's something different yet. So I think spiking neural networks are still under discussions a lot because people do not consider the distributed activity. So still when you are considering to get all the information from a mass storage, it's still not interesting compared to a classical neural network where you have less memory available. So yeah, still under discussion, a lot of forums, and so I don't have the answer to this.
From a perspective on the resistive memories, what does like the static current look like on the various 3 different types of resistive memories?
Excuse me, I didn't get your question.
The resistive memories that you guys have, I think you mentioned 3 different types.
Yeah.
What does the static leakage current look like on those 3?
I can give you some papers, but I don't have a clear figure here to give you. Order of the leakage? No, I don't have. No, really. I can give you some figures, but here I don't have. No. It's really specific device question. I'm a designer. Now, usually I know the leakage of a transistor, but not yet of that kind of things. There are so many, and the variability is very large, so probably they. But I can give you the figure of RRAM if you want. I have it somewhere.
Thank you.
Thank you.